Gravity has always been the quiet oddball of nature. When Isaac Newton first described it in the 1770s, he did not pretend to know what it truly was. He only gave us a rule about how matter attracts matter. Mass pulls on mass through invisible influence across empty space. Newton avoided any claim about how that influence worked. Even he called the idea absurd. Yet the prediction power was undeniable. Apples fell, moons orbited, and the universe obeyed. Centuries later, Albert Einstein stepped in and reshaped the entire picture. Gravity was no longer a pull. Space and time themselves bend around mass, and objects simply follow the curved path. Gravity becomes geometry. The Earth orbits not because the Sun tugs, but because the shape of space-time tells the Earth where to go. It was a revelation that changed physics forever. The predictions worked beautifully. Mercury's orbit finally made sense. Light curved around the Sun, just as Einstein declared. Black holes emerged as real entities instead of imaginary curiosities. However, something remained deeply unsettling. Every other interaction in physics can be written as particles exchanging effects. Electrons share photons. Quarks pass gluons. The electromagnetic force, the strong nuclear force, the weak nuclear force, all have quantum fields with particles and probabilities. But gravity refuses to fit that mold. We try to quantize space-time, just like we do with the other forces, and the math explodes in contradictions. Space-time geometry does not like being chopped into tiny interacting pieces. When we treat gravity like a normal quantum field, we get infinities that wreck the theory. Quantum mechanics says the universe is granular and uncertain at the smallest scales. General relativity says space-time is continuous and smooth. Each framework has been tested with incredible accuracy in its own domain. Both cannot be wrong, yet together they cannot be right. Physicists have spent more than 100 years trying to stitch these two pillars into one seamless structure. Every attempt has stumbled. String theory promises elegant properties but has yet to deliver clear, testable predictions. Loop quantum gravity constructs networks of quantized geometry, but struggles to recover the familiar world with full certainty. Even proposals like causal dynamical triangulations and many more innovative ideas have not reached a consensus path forward. This conflict makes gravity suspicious. Why is it the only interaction that refuses to be quantized neatly? Why does geometry sit apart from all the quantum fields? Why is gravity so unimaginably weaker than the others? You can hold a paperclip against the pull of an entire planet using a tiny magnet. The strength difference is staggering. Something about gravity behaves fundamentally differently, and that difference may be the key to a deeper truth. There is a growing suspicion that gravity might not be fundamental at all. Perhaps we have been asking the wrong question. The universe often hides simplicity behind illusions. Heat is not a basic property. It emerges from the motion of countless molecules we do not see. Pressure is not a primitive force. It emerges from atoms colliding inside a container. These are emergent effects, not fundamental laws, but consequences of hidden microscopic behavior. What if gravity is like that? A grand illusion created by something more basic. Not a force communicated by particles. Not curvature declared by geometry itself. Instead, a natural outcome of statistics and information. A calculation the universe performs to accommodate all the possible ways matter and energy can arrange themselves. This is where entropy enters the stage. Entropy measures how many microscopic configurations are possible for a system. A system with more options has higher entropy. The second law of thermodynamics tells us that entropy tends to increase as time moves forward. This is not a suggestion. It is a deep rule that shapes everything from melting ice to the evolution of galaxies. Now imagine if the universe uses this rule not just to define the direction of time, but to shape the very structure of space-time. Matter might move in ways that increase the number of possible microstates for the universe as a whole, and we perceive that tendency as gravity. This idea seems outrageous at first, Yet pieces of evidence have been accumulating for decades. It begins with the mysterious behavior of black holes. They are regions sealed from view by intense gravity, yet somehow they store information. They obey laws like temperature and entropy. Their entropy is not measured by volume, but by the area of their surface. This is an astonishing clue. Geometry and information are connected. If black holes tie entropy to the shape of space, then maybe space-time everywhere obeys similar rules. The fabric of the universe might not be fundamental. It might be a statistical average of hidden degrees of freedom we have not yet uncovered. Physicists like Ted Jacobson and Eric Verlinde have pushed this suspicion further. They propose that Einstein's equations, which describe the curving of space-time, might actually be thermodynamic equations in disguise, a sign that gravity is the universe's way of maximizing possibilities. As bold as this sounds, it offers something that all other attempts at quantum gravity have struggled to achieve: a connection between geometry and information that explains why gravity behaves so differently. If gravity emerges from entropy, then its weakness makes sense. Emergent forces are often gentle, yet persistent. They hold everything together without needing direct particles to carry their influence. Placing gravity within thermodynamics also gives us a new path to understand dark matter-like behavior and the acceleration of cosmic expansion. Instead of exotic particles and unknown energies, maybe the answer lies in the statistical drive of information itself. The story is far from complete. There are gaps and controversies. Experiments and observations will decide whether this bold idea survives. But for the first time, we might be witnessing a reinterpretation of gravity that feels as profound as the shift from Newton to Einstein. The search is still young. The clues are subtle, yet the possibility is thrilling. Gravity might be the whisper of entropy, the shape of information, the universe bending itself to allow more ways to exist. Gravity has carried an air of mystery longer than any other part of physics. It seems so ordinary in daily life. We drop a glass and it falls. We feel our weight pressing downward. Planets orbit in steady lines around the sun. Gravity looks simple. Yet whenever we try to look beneath that simplicity, we find the strangest puzzles waiting to be solved. Take the idea of mass itself. In general, relativity, mass shapes space-time, and space-time tells mass how to move. That elegant phrasing hides a deep riddle. Why does mass influence space-time at all? What is mass really? Not in the casual sense of how heavy something feels, but in the fundamental sense of why matter possesses this trait that bends geometry in its presence. Quantum mechanics gives a totally different picture. In quantum theory, mass comes from interactions with a field that pervades the universe called the Higgs field. Particles resist acceleration because they interact with this field constantly. That resistance is what we call inertia. This is a beautiful idea that has been tested to great accuracy in particle physics, but it creates a mismatch. Gravity claims mass is a geometric source. Quantum mechanics claims mass is an emergent interaction with another field. These statements are not obviously compatible. Then there is the problem of singularities. Einstein's equations declare that inside black holes, space-time curves to infinite density. Infinite curvature means infinite energy concentration. Physics cannot allow truly infinite values. Infinities are warnings that our understanding has reached its limit. Something deeper must replace the known laws in such extreme environments. The same thing happens at the start of the universe when everything is squeezed into a tiny region. The Big Bang singularity marks another point where our theories collapse. Physicists hoped for decades that by quantizing gravity in a way similar to other forces, they could remove these infinities. All attempts remain incomplete. The further they pursue a conventional quantum force picture, the more elusive a consistent theory becomes. This is not simply a technical hurdle. It might be nature quietly hinting that gravity is not trying to be a force in the first place. Look again at what happens when entropy is involved. Imagine a room filled with bouncing particles. The more ways they can arrange themselves, the higher the entropy. If a cluster of particles collects in one corner, the number of possible configurations drops. Entropy is lower. The particles naturally spread out to occupy more available positions. That spreading is not a force created by particles exchanging something. It is a result of probability. Systems tend to move from states with fewer possibilities towards states with more possibilities. We experience that as an effect much like a force, but it is not fundamental. It is a consequence of statistics. If motion that looks like a force can emerge from simple counting of microstates in a gas, then maybe something similar operates in the vastness of space-time. Mass might act as a kind of constraint on the universe's hidden, microscopic information. When mass appears in some region, the number of allowed configurations drops. The universe responds. It rearranges geometry so that objects move into positions that restore or increase the total number of microstates. We see that rearrangement as gravitational attraction. This line of thinking does something important. It links a cosmic scale puzzle with everyday thermodynamic rules. Instead of asking how particles of gravity push or pull through space, we ask how information flows and equilibrium seeks to reassert itself. This idea feels slightly philosophical until one realizes it makes concrete predictions. Entropic forces have measurable consequences. Still tensions exist. Gravity seems very smooth across space. Thermodynamic effects usually show fluctuations and noise because they depend on random microscopic details. Why does gravity appear so perfect if it comes from underlying random behavior? The best answer so far is that space-time might involve such an enormous number of microscopic degrees of freedom that any randomness cancels out, and the smooth average is astronomically precise. Much like the calm surface of the ocean hides the restless dance of many countless droplets. The deeper we push this reasoning, the more philosophical questions arise. If gravity is statistical, then space-time temperature might exist, yet we do not feel warmth from empty vacuum. Although even that statement becomes uncertain when we recall that accelerated observers detect something called the Unruh effect. To them, the vacuum does appear warm. Empty space might possess thermal properties we only notice under the right conditions. This circle of ideas has led many physicists to wonder whether space-time itself could be emergent. Not a fabric that exists on its own, not a stage where physics takes place. Instead, something built from an enormous number of unseen components. Just as water is not a fundamental substance but emerges from molecules, just as pressure and temperature emerge from trillions of molecular motions, geometry could emerge from information processing on scales far below our current ability to probe. If that is true, then searching for a graviton particle might be like searching for a single atom of temperature. Gravity may not come in discrete quanta because it is not a particle field in the standard sense. It may be a macroscopic phenomenon resulting from more primitive interactions that do not resemble the fields we know. Those primitive interactions could live in a space without geometry and without time in any familiar meaning. Space and time could be the macroscopic illusion created by them. Yet this is not speculation without support. Step-by-step studies of black holes show us that geometry cares deeply about information. The event horizon pulls a boundary around the information we can access, and the area of that horizon measures how much information the black hole hides. That bizarre connection keeps reappearing in theoretical physics. It is as if the universe keeps saying information is real in a physical sense, not just a human idea, something essential to reality's structure. Even when we consider the cosmic expansion, we confront a similar puzzle. Astronomers discovered that the rate of expansion is increasing. Space is stretching faster now than in the past. This accelerating expansion requires something we call dark energy. We do not know what dark energy is, but if space-time emerges from entropy, perhaps the expansion is driven by a thermodynamic push. The universe might be expanding to access greater entropy, to increase the number of possible configurations. These patterns keep adding up. Everywhere we look, gravity behaves like an effect pushing the cosmos towards states, with more available microstates. Instead of a force holding the universe together, it might be the universe trying to expand the realm of possibility. This shift in perspective is enormous. It reframes questions we have been asking for centuries. It challenges the pillars of physics we take for granted. It offers hope that the long conflict between general relativity and quantum mechanics can dissolve if we stop trying to force gravity into quantum clothing. Instead, we might build a new foundation where geometry is not fundamental, where information rules the dynamics. Yet many scientists remain cautious. They insist that a bold idea must confront the universe through observation. Predictions must align with precise measurements. Entropic gravity must pass every test that general relativity already passed. It must also explain the behavior currently attributed to dark matter without invoking mysterious new particles. These challenges are tremendous, but the idea deserves exploration because the clues are too numerous to ignore. The heart of the mystery remains untouched. Why does nature care so much about information? Why should entropy influence the motion of planets and the collapse of stars? What lies beneath the smooth fabric of reality we can measure? There is something deeper waiting to be uncovered, and gravity might be the hint that leads us there. The struggle to understand gravity has always forced us to think bigger. Whenever science has reached a boundary that refused to move, gravity was standing there like a silent gatekeeper daring us to open it. Each time we solved one, mystery gravity revealed another. It acts with infinite range across the cosmos, but is powerless against a tiny magnet on Earth. It shapes the motion of galaxies, yet whispers so softly that on the scale of atoms, it is almost non-existent. Why would a truly fundamental force behave this way? Why would nature make one interaction so overwhelmingly weak compared to the rest? The weak interaction that powers radioactive decay is already many billions of times weaker than electromagnetism. But gravity is trillions of trillions more feeble still. If gravity were just another force of the quantum world, we would expect at least some level of comparable strength. The enormous gulf signals something unique. It suggests that gravity might not originate from the same underlying rules. Perhaps gravity emerges from the collective effect of a vast number of hidden microstates. When a phenomenon emerges from many parts acting together, its influence tends to be gentle but universal. The push of entropy in a gas is not strong on each particle, but dominates the entire system. Gravity could be the universe-wide version of such a push. Think about the bending of light around the sun. Einstein showed that light follows the curvature of space-time itself. But if space-time curvature is an emergent property, then light is responding not to a fundamental force, but to changes in information structure. Where mass exists, the configuration space of the universe changes. Some paths allow more possible microscopic states than others. Photons follow the path that maximizes possibilities, because that is what entropy demands. The bending of starlight is not a pull, but an optimization. If this view holds, then every gravitational event is a kind of information accounting. A star collapsing into a black hole transforms the structure of information so drastically that a new boundary forms, sealing off a region where microstates cannot be accessed. The balance between what is visible and what is hidden shifts. The black hole exterior geometry emerges as the only consistent arrangement that preserves the rule that information must never disappear. Even the radiation that Hawking predicted emerges to ensure that in the long run, information remains accounted for. A black hole may look like a cosmic prison, but in truth, it behaves like a meticulous librarian. Every bit is tracked. None are lost. And this leads to the most startling conjecture. Reality may be encoded. The positions of galaxies, the shape of space-time, the flow of time itself may be surface-level manifestations of deep information interactions. If so, then the familiar three-dimensional world might be a projection, a hologram generated from information stored on two-dimensional surfaces. This sounds like science fiction, until we remember that black hole entropy scales with area rather than volume. the surface knows more than the inside. It counts the microstates. That fact refuses to be ignored. The holographic principle rising from this insight suggests that everything we see in 3 dimensions could trace back to physics operating on some kind of boundary. Our world may appear spacious, but its underlying data may be far more compact. Perhaps the universe is constantly computing new possibilities, and geometry arises as the output of that computation. This would mean that gravity is not a basic ingredient in the cosmic recipe. Gravity would be a result of how the computation arranges outcomes to maintain the relentless drive toward higher entropy. The second law of thermodynamics, the one law that never bends, might be the true architect of the cosmos. Entropy rises because the universe keeps allowing more ways for existence to arrange itself. Gravity would be the visible signature of this unseen priority. It guides matter to cluster into stars and galaxies. That clustering looks like a decrease in disorder, but it opens new channels for complexity to grow. Stars ignite, heavy elements form, planets coalesce, life appears. New forms of entropy generation emerge from the very structures gravity helps to create. The universe is not drifting towards stillness. It is building engines to accelerate entropy production. Gravity is one of those engines. So we stand here with a suspicion. What if the fabric of space-time is a mirage? What if the curvature we measure is just the macroscopic smoothing of deeper processes? What if motion itself is the consequence of the universe rearranging its internal bookkeeping? When you drop a ball, the path it takes is not chosen by a fundamental force pulling downward, but by a necessity to maximize possibilities as it moves. The ball falls because there are vastly more microstates available in lower positions. The universe simply favors the states that have more possibilities. If this picture is correct, then the unification of physics may not come from squeezing general relativity and quantum mechanics into one formula. It may come from stepping back and asking a different question. What are the microscopic constituents of space-time? What rules govern their interactions? How does information weave geometry as an emergent fabric? These questions feel uncomfortable because they rewrite our sense of what is real. Space and time that feel so concrete might be negotiable abstractions. Yet this possibility does not diminish the beauty of general relativity. Instead, it gives Einstein's equations a grander role. They become powerful approximations describing the thermodynamic equilibrium of spacetime. When the microscopic details settle into balance, the geometry they produce obeys the law Einstein discovered. His theory remains a towering achievement, but it might not be the bottom floor of physics. It could be the elegantly decorated second floor built on foundations we are only beginning to uncover. In this vision, gravity finally fits. It refuses to be quantized because it does not belong among the quantum forces. It is not weak because it is flawed, but because emergent effects often are. It handles the grandest cosmic architecture because entropy acts on everything. It may even solve the mysteries of dark matter and dark energy, not by adding unseen substances, but by refining how information shapes space. The road ahead will be difficult. Evidence must be gathered. Experiments must be designed that reveal subtle signatures of emergent gravity. Competing ideas must survive rigorous tests. But the promise of explaining gravity as a thermodynamic consequence could reshape the future of physics. It might solve the riddle that has blocked us for more than 100 years. We have reached the end of this first chapter, and we have only taken the opening steps of a journey that leads from the familiar surface of space-time down into a realm where information is the true currency of nature. Ahead lies the strange landscape of black hole entropy and the discovery that the universe guards information as if it were more precious than energy. Ahead lies the question of whether gravity is simply what happens when the cosmos tries to accommodate more possibilities than its current shape allows. Ahead lies a transformation of our understanding, every bit as dramatic as the leap from Newton to Einstein. Before we dive into the idea that gravity might emerge from entropy, we must understand what entropy truly is. The word carries a reputation for meaning disorder. A broken egg has more entropy than a whole egg. A messy room has more entropy than a tidy one. But disorder is only a metaphor. Entropy is not about mess. Entropy is about how many ways the components of something can be arranged while still appearing the same at the scale we observe. Imagine you hold a deck of cards perfectly ordered by suit and rank. There is only one microscopic arrangement that gives that perfect order. Now shuffle the cards. The deck still looks like a deck, but the number of possible microscopic configurations has become unimaginably large. The shuffled deck has more entropy because there are vastly more ways it can exist while looking like a normal deck. The universe prefers states with more possibilities, not because it likes mess, but because there are more ways to be in such states. Order is rare and fragile. High entropy is common and robust. Entropy also measures information. The more entropy a system has, the less information you have about the exact positions and motions of its parts. If you know a gas occupies a room at a certain temperature, you still have almost no knowledge of the location and speed of any single molecule. There are far too many possibilities. Entropy grows when information about those exact details becomes lost to us or becomes irrelevant to the macroscopic picture. The second law of thermodynamics states that entropy in a closed system never decreases. It can remain constant for a time, but eventually it will rise. Heat flows from hot to cold because there are more microstates available when energy is spread evenly. An ice cube in warm water melts because the combined system of water and ice has far more possible configurations when everything is liquid. The second law is the most unforgiving rule in physics. Every experiment ever made agrees with it. No exception has ever been found. Entropy gives time a direction. Without it, the laws of physics would be symmetric. You could play a film of two billiard balls colliding backward and forward, and the motion would look physically plausible. But once you add heat friction atmosphere particles, cosmic background radiation, and all the ways that energy spreads into smaller details, you start to see an unmistakable direction. A coffee cup cools down, not up. Buildings crumble, not spontaneously assemble. Stars burn fuel and fade, not reverse into pristine hydrogen clouds. Entropy increases. Time follows. So if gravity is linked to entropy, then gravity too may have a direction determined by the flow toward greater possibilities. Gravity pulls matter together into stars and galaxies. At first, that appears like a reduction in disorder. A spread-out gas cloud becomes a tidy sphere of glowing plasma. But something crucial happens inside the star. Nuclear fusion ignites, and the star pours radiation into space. That radiation heats up dust clouds' planets, and in some cases gives rise to life. The entropy increase of all those processes vastly outweighs the entropy loss from the initial clumping. Gravity starts structure, but structure becomes a machine that multiplies entropy. The universe is not choosing order, it is choosing pathways that allow more future options. Entropy does not care what form those options take, it only cares about quantity. A shattered glass can lie broken in millions of arrangements. A living cell can reorganize molecules in countless patterns while sustaining complex processes. A galaxy can host billions of stars burning fuel and spreading energy outward. All these situations create enormous numbers of possible microstates. Complexity can increase entropy faster than chaos can. Life itself may exist because it accelerates the rise of entropy. Biology is a magnificent engine of energy flow. Plants capture sunlight and transform it into chemical structure only to release it again through consumption decay and heat. Every heartbeat, every thought, every breath is part of the inexorable drive toward higher entropy. This raises a new question. What is the underlying reason for the second law? Why must entropy grow? Why does the universe insist on moving from less probable states to more probable ones? Some physicists answer simply that probability demands it. With overwhelming likelihood, systems evolve toward the largest number of configurations. Rare states vanish quickly because there are so many more common alternatives. Entropy is not a force, it is a statistical truth. Yet maybe this statistical truth is a deep physical principle woven into the fabric of existence. The universe began in a state with surprisingly low entropy. Everything was compressed and uniform. There were very few available microstates. That was a strange beginning. Over time, gravity formed structure, fusion released energy, entropy climbed. Now the cosmos is a sea of stars and galaxies with entropy far higher than at its origin. And the climb has only begun. Black holes alone contain unreal entropy. If the universe continues long enough, the total amount of entropy could rise beyond imagination. Entropy is not the enemy of order. It is the architect of structure in the long run. Wherever new pathways open for the universe to explore new possibilities, entropy pushes reality through those doors. The formation of atoms, the buildup of elements, the birth of stars, the chemical dance that leads to living systems and intelligence. Each innovation increases the rate at which entropy rises. The universe might be evolving the ability to rearrange itself in more flexible ways. So here we stand before the idea that entropy might be the true driver of cosmic evolution. A principle deeper than forces, deeper than geometry, deeper than time. And gravity might be the universe's method of expanding access to more states. Instead of thinking of gravity as a pull between masses, think of it as the effect of entropy striving to grow. But if entropy shapes matter, and energy, does it also shape space itself? This is the next step. We have seen that black holes connect entropy to area. The stage on which physics plays out might not be immune to the same thermodynamic rules. Space and time may bend not because of mass as a primitive influence, but because this bending unlocks vastly more microstates accessible to the universe. What hides behind the smooth fabric of space-time? Something granular, something invisible to present experiments, something that stores information, something that responds when matter moves. Those hidden components may obey simple, uncertain rules. When scaled up, they appear as geometry. Geometry then acts like the accountant that tells matter the most entropic path to take. This view is not yet proven. Skepticism must remain. Physics is not a place for wishful thinking. But the connections between entropy and space-time have become too strong to ignore. They repeat themselves in black holes, in cosmic expansion, in the quantum vacuum, even in the act of acceleration itself. The clues all point toward a reality where entropy is king, and gravity is its loyal result. Entropy is so deeply woven into everything that it shapes reality, even when we do not recognize its presence. A cup of hot tea cooling on a table obeys the same law that guides the evolution of galaxies. At every scale, the universe marches toward configurations that can be realized in more ways. This quiet rule defines what is possible and what is forbidden. It defines what future paths remain open and which collapse into impossibility. If the universe is always seeking the largest number of microstates, then everything happening around us becomes a vast negotiation of information. Consider even something as simple as diffusion. A drop of ink in water spreads until the color is evenly distributed. Not because the ink knows where to go, but because the number of possible arrangements explodes when molecules disperse. At the microscopic level, nothing pushes them outward. Statistical certainty pushes them without pushing. They move because any other outcome is overwhelmingly improbable. This viewpoint shakes the foundations of how we think about cause and effect. Forces like heat pressure and buoyancy are not fundamental actors. They are emergent consequences of entropy. A gas pushing against the sides of a container is simply countless particles bouncing in all directions. Their motions are random, but the sum of their actions creates a predictable result. That result feels like a force, but no such direct force exists in the microscopic description. Instead, it is the universe exploring allowed configurations. Imagine now that we extend this reasoning to space-time. What if space-time is not a fixed container, but a dynamic network that adjusts itself in service of entropy? The shape of space could be determined by how many microstates exist within that shape. If certain geometries allow more ways to arrange energy and information, then the universe will prefer them. Curvature would not be commanded by mass. Curvature would be commanded by statistics. Under this light, the presence of mass does not bend space-time by decree. It restricts the number of microstates available in the surrounding region. The universe corrects this restriction by reshaping geometry and redistributing matter into arrangements that restore access to more possibilities. We perceive this correction as gravitational attraction. The universe is updating its bookkeeping to honor the second law of thermodynamics. The more closely we examine entropy, the more we notice that information plays an equal role. In the deepest sense, these ideas are two sides of the same coin. Entropy measures the amount of information that is missing about the microscopic details. Information represents the choices that reality has made about those details. When entropy rises, information about the exact configuration becomes less knowable. The universe hides its specifics, but expands its flexibility. There is a beautiful relationship here. When you gain information about a system, you reduce its entropy because you narrow down the number of possible microstates. When you lose information, the entropy rises. This balance is literal in the mathematics of thermodynamics, and it hints at something profound. Perhaps the universe is not simply matter and energy. Perhaps the universe is fundamentally information chasing new ways to express itself. Think about the flow of time again. We feel time moving forward. We do not feel time move backward. Our memories record the past, but not the future. All of this asymmetry emerges because of entropy. In the early universe, entropy was low. There were fewer paths the cosmos could take. As entropy increases, the number of available futures grows larger and larger. The direction of time is the direction in which the universe discovers more possibilities. Time itself may not be a primary ingredient, but a product of information change. If time and entropy are linked, then gravity might also be linked to the arrow of time. Where gravity acts strongly, we often find intense entropy production. Black holes swallow matter and erase its details from our view while encoding that information in horizon area. Stars burn fuel that spreads heat through space. Galaxies collide and scramble their structure into chaotic patterns. Gravity seems to guide matter into scenarios where entropy can rise faster. All of this suggests a tantalizing idea. The universe may not just be expanding in size, it may be expanding in possibility. Every merger of galaxies, every birth of a star, every chemical reaction increases the options available for what can happen next. And the rise of possibility is precisely the rise of entropy. Yet a puzzle remains. If entropy always rises, why did the universe begin in such a low entropy state? Why did the cosmic story start in a rare condition? Many theories attempt to answer. Perhaps inflation smoothed the early cosmos into simplicity. Perhaps the universe originated in a structure we cannot yet imagine. Perhaps the laws of physics themselves enforce a kind of reset at birth. Whatever the reason, the fact remains that the universe began with enormous potential for entropy growth. Gravity has been helping unlock that potential ever since. Entropy does not only measure physical arrangements, it measures freedom. Freedom for energy to flow, freedom for atoms to bond, freedom for systems to adapt and change. When life emerged on Earth, something extraordinary happened. Organisms learned to harvest energy from the environment and accelerate entropy production even more efficiently. Photosynthesis captures sunlight and transforms its order into heat and chemical motion. Animals consume plants, and chemical bonds are broken and remade. Conscious intelligence develops technologies that reshape entire planets. Entropy increases faster when complexity rises. Could this be an underlying tendency of the universe? Not toward disorder, but toward exploration, toward innovation, toward higher levels of organization that enable more dramatic entropy flow. If that is true, then humanity is not an anomaly. We are part of the universe's thermodynamic evolution. Our curiosity, our creativity, and even our science might be tools the universe uses to discover new states of existence. And gravity gave us the structures needed to begin that journey. So we begin to see entropy not as decay, but as destiny. It drives the cosmos to unfold from simplicity into complexity, from particles into stars, from stars into chemistry, from chemistry into a life, and from life into minds that can ask questions like, why does gravity exist? Entropy wants more microstates, more futures, more paths, and gravity clears the way. The story of entropy is also the story of hidden information. Every grain of sand, every drop of water, every electron carries endless potential states. We will never know all the details, because storing that information would require more storage than the universe itself possesses. So nature keeps the specifics out of reach. Instead, what we observe are the large-scale results of countless microscopic decisions that occur without our knowledge. Entropy is the measure of those hidden details. It counts the number of arrangements underneath the surface view. When two states look identical at the level we care about, but differ in a trillion microscopic ways, the state with the greater number of options holds more entropy. The second law of thermodynamics tells us that systems shift toward these richer states as time flows. The universe is not lazy. It explores. It spreads. It climbs into higher dimensional regions of possibility. When we connect this idea to space-time, a remarkable transformation happens. Space-time is not simply a container where matter drifts. If the fabric of reality is built from unseen informational components, then geometry is the grand average of their activity. Like the surface of a lake appears smooth, even though every molecule below it moves wildly. What we call space could be the equilibrium result of something deeper and more chaotic. Geometry would then appear precise and continuous only because the universe contains an unimaginable number of microscopic degrees of freedom smoothing every wrinkle. If this is true, then space-time itself has entropy. Different shapes of space-time would allow different numbers of possible microstates. When matter moves, the informational content shifts, and space-time geometry must respond. It changes shape to keep the count of possibilities climbing. Gravity appears not as a force, but as the necessary reshaping of space-time to unlock new microstates. Movement happens along paths where entropy increases fastest. This principle does not need particles pushing or pulling. It only requires that systems evolve toward more probable states. Another astonishing example of entropy's influence hides in the vacuum. The quantum vacuum is not empty. Pairs of particles continually appear and disappear. Tiny fluctuations fill space with subtle energy that cannot be removed entirely. Even when we extract as much energy as possible, a leftover baseline persists because uncertainty demands it. Some physicists argue that this sea of fluctuations might give rise to the geometry of space-time itself. The vacuum could be an ocean of information whose waves form the curvature we call gravity. Yet vacuum energy creates a puzzle. According to our best calculations, the vacuum should possess far more energy than what we measure in cosmic expansion. If we take quantum theory literally and count every mode of fluctuation, the energy becomes so large that space should rip itself apart instantly. But it does not. Something in our assumptions must change. If gravity is emergent from entropy and information, perhaps vacuum energy does not gravitate in the usual way, because gravity does not respond to raw energy alone, but to how energy affects the distribution of microstates. This idea remains controversial, but it hints that emergent gravity might naturally resolve the vacuum catastrophe that plagues standard theory. Entropy also explains why temperature exists. Temperature is simply a measure of how energy spreads among microscopic motions. If a system has high entropy, its energy is distributed widely. If energy is concentrated in a few degrees of freedom, the system has low entropy and feels cold. Now we confront a curious thought. If space-time has entropy, then it should also have temperature. That seems absurd until we recall the work of a scientist named Stephen Hawking. He showed that black holes emit a faint thermal glow called Hawking radiation. Black holes are warm. Their temperature is tiny for star-sized ones, but non-zero. Temperature at the edge of space-time means entropy is waiting there too. The idea of thermal space-time becomes even more striking when we look at observers who accelerate. To someone moving steadily in a straight line, empty space is cold. But to someone accelerating, space appears warm. They would measure a temperature that rises with acceleration. This effect, known as the Unruh effect, is tiny for everyday speeds, but it proves that temperature is relative. It depends on how we observe the vacuum. This discovery supports the suspicion that spacetime has thermal properties even when we cannot feel them. A thermal spacetime built from microscopic information naturally leads to entropic gravity. Temperature gradients cause things to move. If one region of spacetime has more accessible microstates than another, matter will move toward the region with more options. That movement feels like attraction. Geometry adjusts to reflect the shifting balance of entropy. In this picture, gravity is not a primary ingredient. It appears whenever information becomes unevenly distributed. This way of thinking also reshapes the story of black holes. When something falls into a black hole, the universe loses access to the detailed information about that object. But the event horizon grows. The surface area expands and the entropy rises. Information is hidden but not destroyed. It becomes encoded in the geometry. The universe is constantly making sure no bits vanish from existence. Conservation of information becomes as sacred as the conservation of energy. Entropy tells us something else profound. It limits how much information we can store inside a region of space. Only a finite amount of information can fit before the region collapses into a black hole. And that limit is determined by the surface area of the boundary, not the volume inside. This discovery is one of the brightest clues in modern physics. It tells us that the true information content of a region is not found within its interior, but on its surface. The familiar three-dimensional world might be a hologram of data stored on boundaries. The universe might function like a cosmic memory device, where geometry is the map and gravity is the rule that ensures consistency. So entropy is not a minor player in physics. It is a powerful architect shaping everything from tea cooling in a cup to stars collapsing into darkness. It controls time direction. It controls the availability of futures. It may even control the structure of space-time. The more we learn, the more entropy looks like the engine behind every process. It expands the universe not by force, but by opening the door to more possibilities. The second law of thermodynamics might be the deepest principle ever discovered. It might be the reason the universe exists in its current form. It might be the reason we can think at all. And it might be the reason gravity curves the paths of planets and the arms of galaxies. If gravity is the servant of entropy, then understanding entropy at its core is not just a question for engineers or chemists. It becomes the central quest of cosmology. We must ask what hidden information lies beneath spacetime. What microscopic elements store the data that determines geometry? How does the universe count these states and choose among them? And what happens when we reach the edge of what entropy can do? These questions guide us toward the next great revelation. Black holes are not just terrifying traps for matter. They are thermodynamic machines. They reveal the deepest connection between area information and the birth of space-time geometry. They know things, they count, they remember. The door to that mystery opened when Jacob Bekenstein and Stephen Hawking discovered that black holes possess entropy. That realization changed everything. There is a place in the universe where gravity becomes so intense that not even light can escape. A place where the familiar rules of physics seem to fold in on themselves. A place where time slows to a crawl and space collapses inward. We call these places black holes. For a long time, they were treated as simple ends of physical meaning. Objects cross the event horizon and vanish, their details gone forever. A black hole was assumed to be the ultimate eraser of information, but that assumption contained a hidden contradiction that would reshape our understanding of the universe. It began with a question asked by a young physicist named Jacob Bekenstein in the 1970s. He wondered whether black holes obey the laws of thermodynamics. Thermodynamics is supposed to apply everywhere. Every physical system should have entropy. Entropy counts the number of microscopic configurations hidden under our macroscopic view. If a black hole swallows matter that is matter, contains information, then what happens to that information? Is it lost forever? If it is lost, then entropy would suddenly drop. The second law of thermodynamics would fail. But that law is sacred in physics. It has survived every challenge. Bekenstein proposed something outrageous. Black holes must have entropy. Their entropy must increase when they consume matter so that the second law remains safe. But then he asked, how do we measure this entropy? A black hole has no visible interior details. We cannot see atoms or vibrations or anything inside. The only structure we can access from the outside is the surface of the event horizon. So Bekenstein made a bold hypothesis. The entropy of a black hole is proportional to the area of its event horizon, not the volume inside, the area of the surface. That idea sounded almost absurd at first. In every familiar system, entropy scales with volume. A larger room can hold more air molecules and therefore more entropy. More space means more microstates. But black holes do not obey that rule. Their entropy is proportional to their surface area alone. Something extraordinary was hiding in that result. Stephen Hawking at first doubted the idea, but he eventually made a groundbreaking discovery. Using the tools of quantum field theory, he showed that black holes emit radiation. Not much, but a tiny glow, now called Hawking radiation. Black holes have temperature. That means they have entropy, just like Bekenstein predicted. Hawking calculated that the entropy is exactly proportional to the area of the event horizon, measured in incredibly tiny Planck area units. Each unit of area can be thought of as storing a bit of information. Black holes are not empty. They are the densest information storage systems in the universe. This revelation changed physics. Suddenly, geometry and thermodynamics were linked. The shape of space-time itself carried entropy. Einstein's theory of gravity was no longer just a geometric description. It hinted at a deeper informational layer beneath the curvature. Every black hole carries a monstrous amount of entropy on its surface. A black hole with the mass of the Sun would hold more entropy than all the ordinary matter in the observable universe. The numbers are staggering. But they are not fantasies. They emerge from real mathematics that matches real physical principles. The idea that the surface area encodes information leads to something called the holographic principle. It suggests that all the information contained inside a region of space could be stored on its boundary, like a three-dimensional image projected from a two-dimensional film. The interior might be an illusion built from information living on the edges. The entire universe could be such a hologram. This is not metaphor. It is supported by calculations from string theory and from the study of quantum entanglement in spacetimes with negative curvature. The details are complex, but the message is clear. Geometry and information are inseparable. Gravity might exist because spacetime wants to maximize entropy. Black holes reveal this truth most clearly. Another consequence is even more unsettling. When matter falls into a black hole, its information does not vanish. It becomes encoded in subtle ways on the horizon. As the black hole slowly evaporates through Hawking radiation, that information must eventually escape back out. If it did not, then quantum mechanics would be violated because quantum evolution is always reversible at its core. This tension sparked what became known as the black hole information paradox. For decades, scientists debated whether information was truly destroyed in black holes or preserved in some hidden form. Many of the sharpest minds in physics contributed to this struggle. Over time, evidence grew strongly toward preservation. The universe does not allow information to disappear. Even when it seems hidden forever at the edge of darkness, it is recorded. The black hole becomes a librarian of reality. Every detail that crosses the horizon is catalogued in a cryptic code on the surface. This means the event horizon is not a simple boundary. It is a physical system with microscopic degrees of freedom. It has temperature, entropy, and an energy content we can measure through the mass of the black hole. Something microscopic must be living on that surface, even if we cannot see it. And the number of microscopic units scales with the area, not the volume. That one fact keeps repeating throughout gravity research. Why should nature store information on surfaces rather than inside volumes? What physical thing is being counted by horizon area? These mysteries suggest that spacetime itself has a granular internal structure. Quantum gravity might not be a theory of smooth geometry at the smallest scales. It might be a theory of information bits exchanging states, and geometry emerges from that informational dance. Black holes demonstrate that entropy affects geometry directly. When the horizon area grows, gravity responds. When area shrinks during evaporation, the geometry adjusts. All of this behavior aligns with the idea that gravity is thermodynamic, a manifestation of the universe seeking to keep track of its information while allowing entropy to increase. This makes black holes our greatest teachers. They push physics to its limits. They expose the cracks in our assumptions. If we can understand how a black hole stores and manipulates information, we might understand what space-time truly is. We might understand gravity's real origin. There is a powerful hint already visible. The mathematics that connects Hawking temperature black hole entropy and Einstein's curvature equations look strikingly similar to the mathematics of heat flow. Ted Jacobson recognized this connection and took it further. He asked, what if Einstein's field equations are nothing more than thermodynamic identities? And he found something astonishing. But that story belongs to what comes next. When Hawking showed that black holes radiate and therefore must have temperature, he united gravity, quantum mechanics, and thermodynamics in a single phenomenon. Three great pillars of physics overlapped in one object. That overlap was not a coincidence. It was a message. Black holes are where the secrets of reality become visible. The surface area law for black hole entropy suggests that something physical lives on the horizon. Some hidden degrees of freedom exist on that two-dimensional boundary, and they encode everything that falls inside. But what are those degrees of freedom? They are not molecules in any ordinary sense. They are not atoms of space-time that we can directly observe. Yet they behave like the microscopic ingredients of a thermodynamic system. That means geometry itself must emerge from some deeper statistical behavior. This realization changes how we think about information. In ordinary systems, we assign entropy according to the number of hidden microstates inside a region. But for black holes, the information is not hidden deep within. It is stored on the edge. The universe prefers to encode data at boundaries where gravitational effects become extreme. So when something crosses the horizon changes. Information is preserved because the area of the surface records the details in a very subtle form. Although we cannot read that record easily, it remains there. Nothing is ever forgotten. This insight set off a transformation in physics. If black holes obey thermodynamics, then Einstein's geometric picture must be a large-scale approximation of something microscopic. Just as the pressure of a gas arises from many molecules pushing outward on the container walls, space-time curvature may arise from many unseen components adjusting themselves in balance. What we call gravity could be the result of those components trying to maximize their entropy. The mathematics of this connection becomes even clearer when we think about what happens right at the horizon. Suppose you hover just outside a black hole using a powerful rocket. The closer you get, the harder you must push to resist falling inward. You feel an increasing heat from the acceleration. This is related to the Unruh effect, where acceleration turns empty space into a thermal bath. Near a black hole horizon, this effect becomes enormous. The horizon appears hot because the conditions there create a strong gradient in accessible microstates. Heat flow across the horizon resembles the flow of information. When energy crosses into the black hole, the surface area grows in proportion to the lost information. Gravity responds by adjusting the shape of space-time. everything is linked. Energy, entropy, and curvature work together as parts of a single system. They are not separate ideas. They are different descriptions of the same underlying reality. Physicists realized that the equations relating black hole entropy and temperature closely resemble the first law of thermodynamics. This law says that changes in energy are linked to work done and heat exchanged. For a black hole, a change in mass, which is its energy, corresponds to a change in surface area, which is its entropy, and a change in curvature, which is something like pressure or work in the geometric sense. Einstein's equations emerge when you treat the horizon as a thermodynamic membrane. That is a clue so powerful it is impossible to ignore. This discovery told us something astonishing. Gravity might not be a fundamental force. It might be a statistical result. The bending of space-time might arise from temperature and entropy, just as steam pressure arises from the random motion of water molecules. The black hole horizon becomes a laboratory where we can see the thermodynamic nature of gravity laid bare. Another important idea emerges from the way black holes communicate through radiation. Hawking radiation seems random, but must encode the information that fell inside in a scrambled form. At first, scientists believed the information might truly be destroyed. That belief would have broken quantum mechanics. But over time, solutions emerged that allow the information to escape again, albeit encoded in patterns far too subtle for us to decode. Black holes do not violate unitarity, the principle that information always flows forward through time. They uphold it, they defend it. In this sense, black holes become guardians of quantum laws. They ensure that the universe never throws away information. Even during the most violent processes, when matter is crushed by gravity into a point-like region, nature finds a way to preserve the record. It may become unreadable to us for a long time, but the universe has perfect memory. This perfect thermodynamic behavior suggests black holes are not pathological breakdowns of physics, but natural elements of a deeper theory. They reveal what space-time looks like when entropy is pushed to its extreme. They expose the information-carrying capacity of space itself. They demand that we rethink geometry as something that emerges only when many bits of information arrange themselves in stable patterns. There is something else almost mystical about the area law. It implies that the true degrees of freedom of space-time do not live inside the bulk. They live on the boundary. This idea blossomed into the holographic principle. When fully developed, this principle suggests that the entire universe may operate on similar rules. Every region of space may be described by information stored on its surface. What we call three-dimensional space may be a projection from two-dimensional data. The boldness of this idea is matched by its evidence. Certain kinds of spacetimes that resemble the interior of anti-de Sitter realms are fully describable by conformal field theories defined on their boundaries. This equivalence, known as ADS-CFT, indicates that gravity in higher dimensions can emerge from quantum information living on a lower dimensional surface. In that formulation, gravity disappears from the fundamental description entirely. It is a byproduct, so black holes became the first proof that information dictates geometry. They became the first evidence that gravity responds to entropy. They became the first windows into the idea of a holographic universe, and they became the first demonstration that space-time might simply be how the universe organizes the unimaginable amount of information that exists within it. There are mysteries still unsolved. What exactly are the microstates counted by black hole entropy? Are they strings? Are they quantum bits of space-time? Are they something we have not yet imagined? These questions lead us into the next breakthrough when a scientist named Ted Jacobson showed that Einstein's field equations can be derived from simple thermodynamic reasoning. Not assumed, derived. His discovery ties the entire fabric of space-time directly to entropy and information in a way so elegant and unavoidable that the idea of gravity as fundamental becomes increasingly suspect. If space-time obeys the laws of heat, then the universe might not be a cold geometric construct. It might be a thermodynamic organism exploring every possible path it can take. The connection between black holes and information forces us to confront a radical shift in how we see the universe. In the old picture, gravity was a simple geometric rule. Mass warps space-time and objects follow the curves. But now we see that these curves are not arbitrary. They serve a purpose. They preserve information. They allow entropy to rise. Space-time is not just a shape. It is a system that responds to the demands of thermodynamics. Imagine the surface of a black hole as a vast information processor. Every particle that falls in changes the state of the horizon. Even if we cannot track the complexity of this process, the universe can. It never loses track. The horizon area increases only in precise amounts that match the new information hidden behind it. This strict accounting reveals an unseen structure that must exist beneath the mathematics. Something real counts those microscopic changes. Something physical stores the data. That hidden something might be the true foundation of space-time. The idea that information is preserved even inside a black hole leads to surprising consequences. For instance, if a black hole has maximum entropy for a given volume, then any attempt to squeeze more information inside must cause the surface area to grow. That is why black holes expand when they absorb matter. It is not just mass piling on. It is information requiring more storage, and nature refuses to break that rule. Now consider black hole evaporation. As Hawking radiation streams outward, the horizon shrinks. The black hole loses mass and energy. Yet somewhere within that radiation, the scrambled information must appear again. That recovery might take longer than the age of the universe for the largest black holes, but the principle remains firm. Information eventually returns. The history of everything that fell into the black hole is not erased but transformed into the most obscure encryption imaginable. Quantum theory insists that the universe is a closed ledger. Nothing is ever crossed out. As strange as this sounds, it brings clarity to one of the most puzzling questions in physics. What happens to information at the ultimate edge of gravitational collapse? The answer is that the event horizon becomes a library of the universe written in patterns far too subtle for us to decode. That is not poetic exaggeration. It is a literal physical statement supported by calculations that connect quantum theory and general relativity. Black holes are the most extreme example of what might be happening everywhere in the cosmos. Every region of space has a limit on the amount of information it can store, and that limit is set by its surface area. If we try to cram more states into a region, then its surface can support gravity intervenes. The region collapses into a black hole, so the information moves to its boundary. This rule shows that geometry emerges not from empty nothingness, but from a saturation of information. Space-time does not allow more detail than its surface can describe. This perspective forces us to rethink what emptiness means. A vacuum is not a void. It is a sea of possible states. Even when no matter seems present, the fabric of space-time still contains information. Virtual particles flicker into existence. Fields fluctuate. These fluctuations contribute to the total entropy of space. The horizon of a black hole simply marks the boundary where information becomes encoded in area rather than volume. But the principle that area stores entropy does not stop at black holes. It extends to any region surrounded by a boundary. So gravity itself seems tied to the way boundaries store information. When the distribution of matter changes, the balance of microstates shifts and space-time curvature adjusts. The universe rearranges its geometry to maximize entropy while preserving the total amount of information. Gravity, in this view, is the thermodynamic response of the holographic encoding of space. All of this suggests that space might not be the fundamental arena after all. Instead, the horizon might be the primary stage. The interior could be a secondary construct emerging from the data written on its surface. This is exactly what the holographic principle claims. The three-dimensional world we move through could be a grand illusion, created by information processing across two-dimensional boundaries we cannot directly perceive. This possibility startled the physics community. It challenges our intuition about what is real. Yet the mathematical successes of holography are not easily dismissed. Entire landscapes of string theory calculations rely on the idea that a higher dimensional gravitational world can be replaced by a lower dimensional non-gravitational one. Geometry in the higher dimension arises because of quantum interactions at the boundary. Gravity emerges from information. If this principle applies to our accelerating universe, then the cosmic horizon might encode everything within the observable region. The expansion of space might reflect the growth of accessible microstates on that horizon. Dark energy, the mysterious driver of cosmic acceleration, might be a thermodynamic pressure pushing the universe toward ever greater entropy. These ideas remain speculative, but they align with more and more clues. Black holes reveal the thermodynamics of space-time. They teach us that information cannot vanish. They show us that entropy is stored not inside volumes but on surfaces. They hint that geometry is subordinate to information. They demonstrate that gravity might be the statistical behavior of microscopic degrees of freedom we have not yet directly seen. Yet for decades, these insights remained philosophical curiosities. They did not give us new equations to replace Einstein's. They did not unify quantum theory with general relativity in a practical way. Then something remarkable happened. A quiet but profound advance reshaped the entire conversation. A physicist named Ted Jacobson asked a daring question. If black hole horizons obey thermodynamic laws, why would that thermodynamic behavior appear only there? Why not everywhere? Why not for any tiny patch of space-time? He imagined taking a small region of space, a horizon, for an accelerating observer and applying the same heat flow rules that describe black hole surfaces. He looked at how energy moves across that small horizon and how entropy changes in response. From those simple thermodynamic considerations, he derived Einstein's field equations. Not assumed. Derived. Space-time curvature emerged automatically as a condition for entropy to behave correctly. This was a breakthrough of startling elegance. It meant that gravity is the thermodynamic behavior of space-time. Einstein's equations are an equation of state, like the ideal gas law. They describe macroscopic balance, not microscopic detail. The true underlying physics must be something else, something like molecules for geometry, something that stores and processes information in vast numbers. Jacobson's result was the strongest sign yet that gravity is emergent. It is not fundamental. It arises because space-time has microstructure, and that microstructure obeys thermodynamic rules. Black holes had hinted at this truth. Jacobson turned that hint into a mathematical fact. Once we see gravity through this lens, the world looks different. We begin to wonder whether every movement of matter is just the universe reorganizing information, whether time flows because entropy demands it, whether space-time stretches and bends because the second law commands it. Gravity might simply be the bookkeeping of the cosmos, making sure every possibility is explored. Black holes are no longer terrifying monsters at the edge of understanding. They are our guides. They are windows into the true nature of gravity. They show us how information shapes geometry. They challenge us to rethink what space and time really are. And they lead us into the next chapter where thermodynamics gives birth to Einstein's equations and reveals that the geometry of the universe is a statistical mirage. The discovery that black holes possess temperature and entropy did more than confirm that horizons have hidden microstates. It whispered a deeper truth. If the most extreme gravitational objects in the universe behave like thermodynamic systems, then maybe all of space-time does. Not just where gravity is overwhelming, but everywhere. Even in the calm, quiet vacuum around us, perhaps geometry is a thermal medium responding to invisible information flow. Ted Jacobson was among the first to see this possibility clearly. In the year 1995, he asked a simple but daring question. What if Einstein's curved spacetime is not a fundamental structure, but a collective effect like pressure or temperature? What if the equations of general relativity are not laws of nature in the deepest sense, but instead rules that emerge from the thermodynamic behavior of spacetime's unseen microstructure? Jacobson knew that if this were true, then the field equations should be derivable from the same principles that govern heat. He began his reasoning not with planets or stars or black holes, but with a tiny patch of space-time. Imagine a small region that for an accelerating observer appears to have a horizon cutting off part of the universe from view. This observer would sense warmth even in perfect vacuum because acceleration produces a thermal bath through the Unruh effect. The horizon they perceive is similar to a miniature black hole boundary. It has temperature. It must also have entropy. Jacobson considered what happens when energy flows across that local horizon. When a bit of matter crosses the boundary, the observer loses access to its detailed information. Entropy changes, and because horizon entropy is tied to area, the geometry near that boundary must adjust. This small shift in geometry represents curvature. It is the bending of spacetime that general relativity describes. Jacobson connected the change in entropy to the change in area and linked both to the energy crossing the patch. What emerged from that thermodynamic analysis were Einstein's equations. The result was stunning. The geometry of spacetime did not need to be postulated at the beginning. It came out automatically once he assumed that horizons have entropy and satisfy the first law of thermodynamics. Energy in equals heat times temperature. A familiar rule from everyday physics gave birth to the mathematics that describes planets orbiting suns and galaxies swirling in cosmic spirals. General relativity was revealed as a thermodynamic equation of state. It describes the large-scale behavior of an underlying information system that is invisible to us. This changes everything. Historically, we believed that spacetime curvature was fundamental. That mass told geometry how to bend by some intrinsic property of matter. But Jacobson showed that curvature is a secondary effect. When energy moves and information becomes inaccessible, horizons adjust to preserve the balance of entropy. Gravity is simply the universe responding so that the second law remains intact. This is not a metaphor. It is a literal physical correspondence. If gravity emerges from entropy, then the microscopic reality beneath spacetime must be storing information in unimaginable quantities. There must be degrees of freedom that count the hidden states of geometry. We do not yet know what those degrees of freedom are. They might resemble quantum bits or strings, or networks of entanglement. But whatever their nature, they obey statistical mechanics. They produce temperature and entropy. And spacetime geometry is the smooth average of their collective activity. Think about this perspective. Pressure in a gas is not a fundamental force. It appears because countless molecules collide with the walls of a container. Temperature is not a basic field. It arises from the distribution of microscopic motion. If we were tiny beings capable of seeing individual molecules, the concept of pressure would disappear from our vocabulary. We would simply see particles bouncing. Gravity could be exactly like that. If we ever gain the ability to look at the microscopic fabric of spacetime directly, the idea of spacetime bending may vanish. We would see information being rearranged and entropy being optimized. This emergent picture also clarifies a long-standing puzzle. Why is gravity so weak compared to other interactions? If gravity were a fundamental force like electromagnetism, it should have a comparable strength. But electromagnetism operates through particle exchange via photons, while gravity has no such messenger in its classical interpretation. If gravity is not a primary interaction, but a statistical effect of many hidden microstates, then its softness makes sense. Emergent forces tend to be gentle because they represent the collective influence of enormous complexity. They do not push directly. They guide outcomes by shaping the allowed paths. Jacobson's work sparked a new way of thinking about physics. Instead of trying to quantize gravity by force, perhaps we should explain geometry itself as information. The curvature of space would then be the visible signature of microscopic correlations. Time would be linked to entropy increase. The speed of light could arise as a property of the information flow in the underlying structure. Everything we think is fundamental might be the macroscopic language spoken by something much more basic and much more mysterious. This approach reverses the hierarchy of physics. Geometry is no longer the starting point. It is the final outcome. Thermodynamics takes the crown. The second law becomes not just a rule about heat, but the architect of space-time. The arrow of time, the formation of horizons, the acceleration of the universe, all become consequences of entropy's relentless rise. Black holes first gave the clue by teaching us that information saturates horizon area. Jacobson widened the clue into a general principle that applies everywhere. Even the smallest sliver of space obeys the same thermodynamic rules as a black hole surface. Gravity is the same phenomenon on every scale. The universe is a single information network, and curvature is its accounting system. This realization invites new questions. If space-time is emergent, then what is it emerging from? What is the deep structure that encodes information? How does it rearrange itself to increase entropy? What does locality mean if space is just a convenient approximation? Do we live inside a giant computation where the laws of physics are the processing rules? Jacobson's insight does not answer those questions, but it points us toward them with undeniable clarity. It tells us that the path to quantum gravity is not through brute force quantization of curvature. That path has resisted progress for more than 100 years because it might be aimed at the wrong target. Instead, we must uncover the microscopic statistical mechanics that produce space-time and gravity as emergent properties. We must discover the informational atoms of the universe. This transition in our understanding may be as profound as the moment when physicists realized that heat does not come from fire spirits, but from molecules. It may be as revolutionary as the discovery that pressure is not a primitive force, but the average effect of collisions. Now we suspect that gravity is not a law commanding bodies to fall, but the universe maximizing its possibilities. As strange as this idea seems, it fits the evidence more naturally than the old picture. Black hole thermodynamics becomes a necessary feature, not an anomaly. The weakness of gravity becomes expected, not puzzling. The connection between horizons and information becomes fundamental, not accidental. And the deep compatibility of thermodynamics with general relativity finally makes sense. We have crossed a threshold in thought. Gravity is beginning to look like the shadow cast by a deeper process, a process made of information striving to explore every state it can. Gravity emerging from thermodynamics does not make space-time less real. It makes it more meaningful. Instead of seeing geometry as a silent fixed stage, we begin to recognize it as a living record of everything that has ever happened. Curvature holds the memory of energy flows. The shape of space is a diary of the universe, keeping track of what information has moved and where it has gone. Every ripple of gravity is a change in the cosmic archive. When Jacobson connected the flow of heat across tiny horizons to the bending of space-time, he showed that gravity is simply the universe insisting that information remains consistent. If energy crosses a boundary, then the number of hidden microstates must rise in proportion. Entropy refuses to shrink. Geometry must adjust so that nothing violates the second law. When you drop a stone into water, the surface responds with waves. When energy crosses a horizon, space-time responds with curvature. The analogy is not perfect, but it captures the spirit of this new understanding. Gravity is the reaction of a medium that must preserve balance. This leads to an astonishing reinterpretation of mass. Mass is not something that produces gravity by its very nature. Mass is information restriction. When a chunk of matter sits in some place, the microstates of the underlying structure become slightly less available. The universe corrects this restriction by bending geometry. That bending sends nearby objects drifting into positions that restore a larger number of possibilities. Gravity is a gentle push toward freedom. It allows matter to move in ways that unlock more ways the microscopic states may arrange themselves. We can test this view by looking at the equivalence principle. This principle states that inertial mass and gravitational mass are exactly the same. A feather and a stone fall together in a vacuum because the effects of acceleration and gravity cannot be distinguished. In the thermodynamic picture, this equality is no coincidence. Inertia is resistance to changes in the pattern of information. Gravity is the tendency of information to reorganize for greater entropy. The identity of these two masses becomes natural. They are two faces of the same phenomenon. One describes how matter interacts with the underlying information field. The other describes how the field responds in return. There is also a beautiful harmony in how gravity relates to forces like electromagnetism. Light and matter exchange energy through photon interactions. These exchanges carry detailed information about fields and charges. Gravity does not act through such precise channels. It works broadly. It favors the overall growth of microstates, not the specifics of particle identity. That is why it cannot be shielded. No matter what you do, gravity still acts. All matter contributes to the accounting of entropy. There is no way to hide from thermodynamics. Now imagine zooming far down into the smallest scales of space-time. At those depths, the smooth geometry described by Einstein dissolves into something far stranger. Many theorists believe we would find a network of information links, not points in space, but bits connected by relations. Not curves, but entanglement patterns. If this picture is correct, then distance itself may emerge from how strongly those bits are correlated. Closer objects are those whose information networks overlap heavily. Farther objects are those whose correlations are weak. Space could be a map of information connectivity. If space is a network built from information, then time emerges from changes in that network. Time is the rate at which information becomes unavailable to the current description and more widely distributed among possibilities. The arrow of time is the direction in which entanglement spreads. Entropy is the measure of how much information has leaked beyond what we can observe, and gravity is the tendency of this spreading to reshape the large-scale structure of the world. This paints a universe where nothing is static. Even empty space crackles with motion and uncertainty. The vacuum becomes an active participant in the thermodynamic evolution of reality. Temperature gradients appear when horizons limit access to bits. Forces arise from the bias of entropy seeking growth. Curvature emerges like a statistical tide moving matter along the most probable paths. Jacobson's idea also explains why general relativity works so incredibly well at large scales. When the number of microstates involved becomes astronomical, the thermodynamic average becomes nearly perfect. Fluctuations are drowned by sheer volume. Space-time appears smooth and continuous. But on tiny scales near the Planck length, where only a few bits of information might define a region, geometry would become wild and uncertain. That is why general relativity breaks down at singularities. It is like trying to describe a handful of molecules with the theory of pressure. The scale is too small for the approximation to hold. This is not a failure of Einstein's theory. It is a clue, a nudge telling us to look for the deeper structure. That structure must be quantum in nature, because information is a quantum concept. Quantum entanglement might be the glue that forms space-time. When bits of information become correlated, the universe builds a geometric bridge between them. When entanglement fades, distances grow, space swells. Expansion might arise from the gradual loosening of informational bonds over cosmic time. Even the cosmological constant which drives the acceleration of the universe's expansion could emerge from these microscopic rules. Perhaps the vacuum has a certain baseline entropy that must increase as the universe grows. The horizon of the observable cosmos expands. and with it the number of accessible microstates. The push we call dark energy may simply be thermodynamics unfolding at the larger scales. It might be the same rule that melts ice or powers stars, but applied to the cosmos itself. When we accept that Einstein's equations arise from heat, we must accept that heat knows more about the universe than geometry does. Thermodynamics keeps winning battles in physics. It explains why black holes must radiate. It clarifies why time flows forward. It predicts how complexity evolves. And now it threatens to demote gravity from its throne as a fundamental interaction to a remarkable but emergent one. This shift in perspective does not diminish the elegance of general relativity. It completes it. It shows us why Einstein's equations have the form they do. It gives them context inside a larger and richer story. Geometry becomes a visible shadow of information seeking freedom. Curvature becomes the bending of possibility. Gravity becomes the silent accountant of entropy. As we move deeper into this line of thought, one name begins to rise. Eric Verlinde, a physicist who took Jacobson's insight and dared to push further. If gravity emerges from entropy, then perhaps we can rederive the familiar gravitational pull from purely thermodynamic reasoning. Verlinde proposed that the attraction between masses is not a force at all, but the result of information shifting to maximize the number of hidden microstates. He called it entropic gravity, and he believed it could even explain the puzzling motions of galaxies without invoking dark matter. His proposal stunned the physics community. It divided opinions. Some saw a bright new path. Others saw speculation reaching too far. But his calculations offered something much needed in this arena. They gave testable predictions. They offered a guide for the next step. Jacobson revealed that Einstein's curved spacetime can emerge from thermodynamic rules. Yet his approach still relied on the full structure of general relativity to express the microscopic heat flow. It showed that gravity behaves like entropy, but did not fully explain how the familiar pull between masses arises as an entropic effect. That is where Eric Verlinde entered the story. Verlinde asked a question so direct that it felt almost like a challenge. If gravity is not fundamental, but emerges from the tendency of systems to maximize entropy, then can we derive Newton's law of universal gravitation purely from information? No mention of space-time curvature, no reliance on the Einstein framework, just the simplest rule in physics: entropy increases. To explore this idea, imagine a test mass approaching a larger mass. Quantum information about the position of that test mass becomes less accessible as it gets closer to the larger object. The degrees of freedom of the underlying microstructure become constrained. That loss of accessible microstates means the entropy of the universe drops slightly. Nature reacts immediately by trying to reverse that drop. It pushes the test mass outward, but the larger mass's own presence continually shifts the entropy landscape. There exists a stable configuration where the motion that restores entropy best is the motion we observe as gravitational attraction. In Verlinde's reasoning, the familiar force of gravity is not transmitted through space. It is not carried by particles. It is not inscribed in geometry. It is entropic. It arises when matter moves in ways that increase the number of accessible microstates for the universe as a whole. The mathematics he developed for this idea is not merely conceptual. From the simple assumption that information changes when a particle moves relative to a holographic surface, he derived Newton's inverse square law for gravitational pull. The same law that Newton inferred from falling apples and orbiting moons appears automatically from entropy. That is extraordinary. Here, gravity behaves exactly like an entropic force. Consider a stretched elastic band. When it contracts, it pulls objects together. But that pull is not a fundamental interaction. It arises from the thermodynamic behavior of polymer chains inside the band, which try to return to a state of high entropy. You feel a force, but underneath it is statistical mechanics. Gravity might be the universal version of that same idea. matter falls toward matter because the paths that bring them together allow more microscopic arrangements. Verlinder's idea pushes this concept beyond the domain of near-field physics and into the vastness of galaxies. Astronomers long ago discovered that stars near the edges of spiral galaxies move too fast. They orbit as if there is more gravitational pull than visible matter can provide. This mystery led to the dark matter hypothesis. Invisible mass hidden in halos around galaxies supposedly supplies the missing pull. Yet despite decades of searching, not one confirmed particle of dark matter has been found. Verlinder suggested that the flat rotation curves of galaxies might instead reveal a shift in how entropy influences gravity at large scales. Far from the galaxy core, the distribution of microstates in spacetime may behave differently. The entropic force could strengthen slightly compared to Newton's law. Without adding new particles, the motions of stars could be explained as a consequence of information and entropy responding to the shape of the universe. This approach has challenges. Some galaxy observations match Verlinder's predictions. Others seem to resist them. The idea remains under active scrutiny. But the fact that an emergent theory of gravity can even attempt to reproduce these galactic effects is remarkable. It means the entropic viewpoint is not just philosophy. It makes contact with real data. It suggests the invisible might not always be material. Sometimes the invisible is informational. In this picture, what we call gravitational mass becomes the measure of how strongly matter restricts the underlying microstates. More mass means a stronger reduction in entropy, which means a stronger thermodynamic push to correct that imbalance. The inverse square nature of the law arises because the information stored on the surface of a sphere grows with radius squared. The entropy landscape around a spherical mass naturally produces the exact form of attraction we observe. Space is not pulling masses together. Information is. The deeper implication is almost dizzying. Geometry itself might be a derivative concept invented by the universe to keep track of information flow. If the holographic principle is correct, then the world we navigate is already encoded on cosmic horizons. Distances might be bookkeeping rules. Motion might be a way to reconcile entropy balance. Mass might simply be information that has become stubborn to distribute. Emergent gravity also gives fresh perspective on cosmic expansion. The universe grows not only in spatial extent, but in informational capacity. The cosmic horizon expands, allowing more microstates to come into play. That growth could manifest as a repulsive effect on large scales. Instead of dark energy being a strange and separate phenomenon, it might emerge from the same entropy rule that guides falling objects. Gravity and the expansion of the universe could be parts of the same thermodynamic story. This raises profound questions about the nature of existence. If space and time emerge from information, then causality is also an emergent phenomenon. Cause and effect might be the smoothing out of deeper statistical behavior. The laws of physics we treasure for their precision could be approximations that hold only when the number of bits involved is unimaginably high. At microscopic scales, the universe might obey principles that look nothing like geometry or force. Those principles could be digital in character. The cosmos might be processing information like a limitless computer. Yet, like every bold idea, Verlinder's theory faces critics. Entropic gravity must pass the same rigorous tests that general relativity has conquered. It must explain gravitational waves. It must fit precision measurements of planetary orbits. It must account for lensing of distant galaxies. So far, the theory has not answered every challenge, but it has not failed decisively either. It may yet evolve into a deeper understanding that blends the best of both worlds. The strongest virtue of emergent gravity is that it does not struggle against quantum mechanics. It incorporates quantum information at the foundation. Entanglement, which links particles even across vast distances, might be the true fabric of space-time. When entanglement patterns change, geometry bends. When entanglement becomes inaccessible, horizons form. When entanglement reaches equilibrium, Einstein's equations rise into view. Jacobson opened the door by showing that heat produces curvature. Verlinde walked through by showing that entropy produces attraction. Together, their work points to a future where gravity is no longer a mysterious outlier in physics, but a natural outcome of information flow. The universe becomes a thermodynamic explorer, space-time becomes a dynamic encyclopedia, and gravity is the story that emerges when the cosmos chooses the path of maximum possibility. We have reached the end of this chapter. A new vision of gravity is taking shape. It is time to step fully into the realm of holography, where information may be the true substance of the universe, and where our three-dimensional world could be a beautiful projection of hidden data. Erik Verlinde stepped into the conversation with a daring clarity. If black holes and horizons already show that geometry and entropy are inseparable, then gravity itself might arise from the universe seeking states with more possibilities. No invisible pulling force, no fundamental graviton particle, just information shifting to maximize entropy. He imagined a holographic screen, an imaginary surface that encodes information about matter inside it. As a small mass moves closer to that screen, some of the hidden microstates become inaccessible. Entropy goes down. Nature reacts by urging the mass to move in the direction that restores lost possibilities. We feel that reaction as gravitational attraction. This is more than a poetic idea. Verlinde showed that by treating information like this, one can recover Newton's law, where the gravitational pull between two masses falls with the square of the distance between them. From the demand that entropy must rise, comes the equation that guides the moon around the Earth and holds galaxies together. Entropy becomes the architect, and gravity becomes the tool. In this picture, the sun is not pulling the Earth. The universe is quietly encouraging the Earth to move into positions where more microstates are available. Even the orbit itself is the result of a balance in the entropy landscape. The planets dance because information demands a particular arrangement that keeps potential states expanding into the future. Space is not passive. It is always adjusting itself to maintain access to possibility. This shift in viewpoint solves a haunting puzzle. Galaxies spin faster at their edges than visible matter can explain. For decades, scientists insisted there must be invisible dark matter making up most of the mass. They imagined particles that fill halos around galaxies, though none have ever been seen. Verlinde suggested a different path. On enormous scales, the entropy associated with quantum information of space-time itself adds a new component to gravity. That additional entropic influence could boost the motion of stars without any hidden particles at all. Some observations agree with this prediction. Others remain uncertain. The idea is being tested in real cosmic data, and that makes it exciting. Where Einstein showed how geometry shapes motion, Verlinde suggests that the geometry itself is shaped by thermodynamic desire. The universe is not static. It is restless. It is computing. Every interaction, every orbit, every collapse is part of a vast calculation that always points toward increased entropy. Matter moves because information must rearrange. Space curves because horizons must grow. Entropy knows the way forward, and gravity is the whisper we hear when the universe follows it. The deeper we look into space-time, the more the universe hints that what we see is not the full story. Black holes were the first to reveal this with their strange rule that entropy depends only on the surface area of the horizon and not on the volume inside. That one simple fact suggests that the amount of information the universe can store is determined by boundaries, not by bulk. If true, then our familiar three-dimensional world may not be the truest picture of reality. It may be a projection, a hologram written on distant surfaces where the universe keeps its records. To understand this possibility, imagine that every tiny patch of space has a secret twin on a cosmic boundary far away. The position of a star, the path of a planet, even the atoms inside your body could be shadows cast inward from data living on a two-dimensional surface. In such a universe, geometry is not fundamental. The bending of space becomes a kind of visual effect that emerges when the underlying information rearranges itself to increase entropy. Space is not emptiness. It is a story told by correlations among hidden bits. Quantum entanglement gives us a clue about how this story is written. When two particles share entanglement, their fates are linked regardless of how far apart they drift. That link has no thickness. It does not stretch through space like a rope. It is a direct informational connection. If space emerges from such links, then distance itself becomes a measure of how strongly systems are entangled. Close objects are deeply correlated. Far objects have weak or no correlation. Space becomes a map of relationships. In some theoretical models, this idea becomes exact. A world with gravity can be fully described by a different world without gravity that lives on a boundary with fewer dimensions. Every falling rock, every orbit, every ripple of space-time can be translated into quantum interactions on that lower dimensional surface. This is known as holographic duality, and it reveals something profound. Gravity in the higher dimension is simply the thermodynamic response of information in the lower dimension. What looks like a geometric force is an emergent effect of statistics and entropy. This does not mean we are living inside a giant movie or simulation. It means that physical reality might have two equally valid descriptions. One as a world of space-time matter and gravity, another as a world of pure information encoded on surfaces. Both descriptions predict the same outcomes, but one suggests that gravity is not a fundamental actor. It is a product of information spread. The holographic view may also explain the growth of the universe. As the cosmic horizon expands, more surface area becomes available to store information. More microstates become accessible. Entropy increases. That increase could create a gentle outward push that accelerates cosmic expansion. Instead of inventing a mysterious dark energy, the holographic principle would say, the universe is doing exactly what entropy demands. It is making room for more ways to exist. Even the flow of time begins to look different in this picture. Time moves forward because the universe expands its informational catalog. The future contains more microstates than the past. The arrow of time is the direction in which the hologram writes new data. The reason we remember yesterday and not tomorrow is because yesterday's information is already encoded. Tomorrow's is still being created. Our everyday experience hides these strange features. We see objects and distances as real and direct. We touch surfaces and feel solid walls. But these sensations might arise from deep informational rules that only take familiar form when enormous numbers of quantum bits act together with perfect coordination. Geometry feels continuous and smooth because trillions upon trillions of internal links average out to a quiet background. The holographic mechanism is so flawless that only at the edges of knowledge do its hints appear. Black holes are the clearest hint. Quantum entanglement in exotic spacetime geometries is another. The success of holographic dualities in theoretical physics is a third. Bit by bit, evidence grows that the page on which the universe writes its story is not the three-dimensional volume we move through. It may be the distant boundary we can never reach yet, which defines everything we see. It is unsettling to imagine that space might not be what it seems. Yet this view offers something priceless. It brings gravity into harmony with quantum mechanics by removing gravity from the list of fundamental forces. Gravity becomes a consequence, a whisper of information, a smoothing of correlations, a push toward higher entropy. Reality may be deeper than geometry. It may be woven from the logic of information itself. If gravity truly emerges from entropy and information, then the universe must reveal signs of that origin. Every good scientific idea must survive contact with observation. It must explain what we see and predict what we have not yet seen. Emergent gravity and holographic spacetime are bold proposals, but they must pass the same tests that general relativity has mastered for more than a century. Some of the clues already appear in the motions of galaxies. Stars at the edges orbit faster than expected. based on visible mass alone. The standard answer to this puzzle is dark matter, an invisible substance that adds gravitational pull without emitting light. But decades of searching with the most sensitive detectors have failed to reveal any such particles. Emergent gravity suggests a different explanation. At the outer regions of galaxies, the entropy associated with space-time itself becomes important. The information stored in the vast cosmic environment creates an additional entropic pull. In some cases, these predictions match observed rotation curves remarkably well without adding new matter. Other tests come from gravitational lensing. When light bends around massive galaxies or clusters, the amount of curvature reveals how much gravitational influence is present. Emergent gravity must reproduce those distortions with the same accuracy as Einstein's theory. In certain observations, the lensing pattern fits almost perfectly. In others, the match is not yet as strong. The measurements continue, telescopes sharpen, data accumulates. The theory evolves. Then, there is the largest mystery of all. The expansion of the universe is accelerating. General relativity explains this by introducing dark energy, a mysterious form of energy that fills empty space and pushes everything apart. But if space-time is holographic, then the acceleration might come from entropy growing at the cosmic horizon. As the boundary of the observable universe expands, new microstates become available. That expansion of possibility might create a gentle push outward. Instead of dark energy being a strange new ingredient, it might simply be the universe obeying the second law. Still, emergent gravity must do more than reinterpret known results. It must predict something unique. Some researchers study how the motion of small masses in quiet environments might reveal tiny entropy-driven effects. Others examine how entanglement structure might change near black holes. Experiments remain technically difficult, but the effort continues. If a single prediction stands out and is confirmed, the foundation of physics may shift. Critics remain careful and persistent. They argue that dark matter explanations still work more consistently across all cosmic scales. They note that emergent gravity is not yet a complete framework. They insist that theory must be sharpened before it can challenge the standard model of cosmology. These objections are not barriers, they are fuel. Science advances through skepticism. One thing is certain: the union of entropy, information, and space-time has already changed how physicists think. Even if some details of emergent gravity must be revised, the core insight seems too powerful to disappear. Geometry and thermodynamics are connected. Information is physical. And the universe might be less about what things are and more about how many ways they can be. In the decades ahead, new telescopes will map the universe more precisely. Black hole mergers observed through gravitational waves will reveal how horizons behave under extreme change. Quantum experiments may capture tiny signatures of thermal spacetime. Any of these could tilt the balance toward a new understanding, and that understanding would transform what we believe about existence itself. Gravity may no longer be the force that pulls. It may be the universe rearranging itself to make room for more possibilities, and the ultimate test will be whether this view continues to match the truth written in the stars. Time feels like a one-way road. We wake up older than the day before. Stars burn fuel and never reverse the process. A shattered glass does not leap back together. The universe keeps moving forward and never rewinds. This direction, this flow, is something we take for granted. But physics without thermodynamics does not care about direction. The equations of motion in quantum mechanics and in general relativity work perfectly well backward or forward. So why does nature choose a forward arrow? Entropy supplies the answer. The universe began with very low entropy compared to what is possible. There were few allowed arrangements. As time unfolds, more microstates become available and entropy rises. The direction of highest entropy increase becomes the direction we call future. Time is not a fundamental river. It is the sense we have of the universe exploring more and more possibilities. Where entropy leads, we follow. If gravity emerges, From entropy, then gravity might also shape the arrow of time. When gravity pulls matter together, it forms stars, galaxies, and planets. At first glance, that seems like the universe creating order. But within those structures, new ways to increase entropy are born. Stars blaze nuclear fire and pour energy outward. Heavy elements form, break apart, and reform in endless cycles. On at least one planet, life emerged and became a more efficient agent of energy dispersal. Gravity builds engines that accelerate the increase of entropy. The future universe is richer in structure because structure opens new paths for entropy to grow. Think of how collapse and expansion interplay. Gravity collapses matter into dense cores. Thermodynamics responds with pressure and heat resisting the collapse. When collapse wins, black holes appear and store immense entropy on their horizons. When thermodynamics wins, stars ignite and spew radiation that raises entropy everywhere else. Gravity and entropy work together like two voices in the same cosmic choir, guiding the universe towards states with more potential. Time's arrow and gravity's direction might be the same thing. Falling objects move not because they are pulled downward, but because the paths below offer more microstates. The future is downward. The future is where entropy increases fastest. When a star moves through the galaxy, its orbit is not simply a consequence of mass and geometry, but of the universe choosing the trajectory that keeps possibility expanding. If the universe is a grand computation, then time emerges from the processing of information. With every moment that passes, more data becomes encoded into the configuration of space-time. The past is written. The future is undefined. Gravity helps write the next line by guiding matter into arrangements that allow the writing to continue. Even memory is tied to entropy. We remember what leaves records. Records require energy, and energy flow requires entropy increase. Forgetting is easier than remembering because forgetting is more entropic. As the cosmos grows older, entropy will dominate even more. Stars will fade. Black holes will swallow what they can. Hawking radiation will slowly melt them into particles that wander through cold space. In the far future, only the faint echo of quantum fluctuations will remain. Even then, entropy will still rise. The arrow of time will still point toward new possibilities, even in a universe drifting towards stillness. The direction persists, even when change slows. This view turns existence into a story of increasing complexity. The universe did not start organized, it started simple. Gravity then built complexity out of simplicity to accelerate the rise of entropy. Time flows because complexity creates more ways to rearrange the parts. And we, conscious minds who wonder why gravity exists, are participants in this process. Our thoughts transform energy. Our actions increase entropy. Our curiosity adds to the universe's record of itself. Perhaps the universe did not just allow complexity. Perhaps the universe needed it. Intelligence becomes a tool for entropy to grow faster than chance alone could manage. In that sense, the arrow of time may run straight through every living mind, every star, every galaxy. Gravity opens the stage. Entropy writes the play. Time is the act of turning possibility into history. And so, the forward flow we feel is not mysterious at all. It is the sensation of entropy expanding the reach of reality. It is the imprint of countless microstates becoming accessible. It is the future unfolding because more futures exist than pasts. If gravity emerges from information, then our universe might resemble a machine that computes reality. Not a machine built by anyone, but a natural process where information constantly updates itself. Space-time becomes the memory. Matter becomes the stored data. The laws of physics become the operating rules that govern how information can change. Even the expansion of the universe becomes an increase in storage space as the cosmic horizon grows and more microstates become available. In this vision, the universe behaves like a massive system of information processing. Every collision of particles is a calculation. Every movement of a planet is a result of entropy guiding the computation toward new arrangements. The holographic principle tells us that the total amount of information inside a region of space is limited by the area of its boundary. This means that reality does not keep track of every detail everywhere. It only stores the information absolutely necessary to maintain consistency. What we call emptiness is simply space where the information is minimal but still present. Quantum mechanics adds another layer. When particles interact, they become entangled. Their properties are linked through pure information. Space-time may not just hold information. Space-time may be built from entanglement itself. If you connect two regions with entanglement, they appear close. If you remove entanglement, they drift apart. Distances become flexible. Geometry becomes a side effect of information structure. In a computer, the state of each bit contributes to the total memory. In the universe, the state of each quantum entity contributes to the total entropy. The cosmos does not compute answers for anyone, but the computation drives motion and evolution. When a black hole absorbs matter, its horizon grows as if its storage just increased. When stars form, the universe gains engines capable of processing energy more efficiently. Even life can be viewed as an entropy-maximizing algorithm. We capture energy, distribute it, and create more complexity. In doing so, we help the universe explore states it could never reach otherwise. Some scientists propose that the deep structure of spacetime might be a network of tiny information nodes connected through entanglement. In such a network, time is the updating of node states. Gravity is the tendency of the network to rearrange itself toward patterns that allow more freedom in those states. Geometry is just what that pattern looks like when billions upon billions of nodes act together. This idea does not say the universe is artificial. It says the universe is logical. It follows rules of information that appear as laws of physics. If someone could see the deeper machinery, they would not see planets moving through curved space-time. They would see vast webs of entanglement updating bit by bit and using entropy to choose the most likely next step. Reality becomes code that writes itself. As thinkers and observers, we find ourselves inside the very system we attempt to understand. Our neurons fire because ions shift. Those ions shift because forces guide them. Those forces guide because information demands entropy to rise. Intelligence emerges from the universe's drive to expand possibility. Our ability to think may not be an accident, but a direct result of the cosmic computation accelerating itself. If gravity is the thermodynamic rule the universe follows to explore new states, then the formation of minds capable of discovering that rule is part of the same unfolding. We are not outsiders decoding the cosmos. We are components of the process. We are thoughts the universe is having about itself. If gravity is entropic, then the universe is not pushed forward by a pull. It is carried by a need. A quiet, unstoppable need to unlock more ways of being. From the smallest quantum flicker to the rotation of galaxies, the universe seeks configurations with more hidden possibilities. Entropy is not disorder. It is potential. It is the widening of the future. Gravity would then be the grand arranger of reality, creating space for possibility to grow. In the beginning, the cosmos held almost no variety. It was smooth and simple, a uniform sea of energy and a scarcity of allowed microstates. But simplicity is a narrow cage, and the universe sought release. Gravity gathered matter into dense spheres where nuclear fire could ignite. Stars poured energy outward, raising entropy on scales impossible in a uniform cosmos. After billions of years, supernova explosions scattered elements across space. These atoms built planets. Planets built chemistry. Chemistry built life. Life built minds. Minds built stories and tools and knowledge. Complexity did not fight entropy. It increased it. Order is not the enemy of entropy when order creates more paths for transformation. When a planet orbits the sun, that motion looks like a constraint, but it actually opens more futures. the stable pattern of orbiting worlds allows complexity to endure long enough for evolution to unfold. Gravity builds not to confine, but to enable. A universe without gravity might be a uniform fog where nothing interesting ever happens. Gravity gives that fog shape and structure. Structure gives rise to engines of entropy, like stars and black holes. Each structure unlocks more ways for energy to flow and information to be stored. Even collapse serves the grand design. When matter falls inward to form a black hole, we might think that structure is lost forever into darkness. But the event horizon expands, which means the total entropy explodes upward. A black hole with the mass of a star stores more possibilities on its surface than the entire visible cosmos of ordinary matter. Collapse is not destruction. Collapse is amplification. Time itself emerges from this growth. The future contains more possibilities than the past. That is why the future feels open and the past feels fixed. Memory keeps the old states recorded in brains and fossils and background radiation, while the new states wait ahead unwritten. Every heartbeat, every rotation of the Earth, every orbit of the Moon adds more microstates to the cosmic accounting. The flow of time is simply the rise of entropy turned into experience. When we look outward and see distant galaxies rushing away from us faster and faster, it might not be because a strange dark energy is pushing them. It could be entropy at work once again. The cosmic horizon grows to hold more possibilities. Expansion increases the area on which the universe can store information. The faster the horizon grows, the more futures unfold. Expansion may be the breath of entropy. All this repositions humanity in the cosmic story. We are not spectators watching a clockwork universe. We are agents of entropy, helping the universe explore its deepest potential. Every act of thinking redistributes energy. Every tool we create opens new transformations. Civilization expands the reach of possibility. The universe looks through our eyes and learns about itself. We are not apart from gravity. We are expressions of its purpose. As we search for the fundamental laws of nature, we peel back layers of deeper machinery. Beneath geometry, we find thermodynamics. Beneath thermodynamics, we find information. Beneath information, we might one day find the true atoms of space-time. They could be spins or qubits or patterns of entanglement. They could be something stranger than anything imagined. Whatever they are, they count, they store, they arrange, they evolve. And gravity appears when their arrangement shifts to expand the number of allowed states. There is no corner of physics that remains untouched by this possibility. The weakness of gravity compared to other forces becomes natural. Emergent effects are soft because they arise from coordination rather than direct interaction. The unity of inertial mass and gravitational mass becomes expected. Both describe how information responds to change. The existence of cosmic horizons becomes unavoidable. Boundaries are where information is written. And the ultimate fate of the universe becomes a slow but unstoppable diffusion of energy into every possible state. Yet even in a distant future, where stars fade and black holes evaporate, the march of entropy continues. Tiny quantum fluctuations will still appear and vanish. Information will still shuffle itself. Time will still have direction because the universe will still have space for growth. The story does not end in darkness. It ends in transformation. The final truth emerging from all these clues is profound. We do not live in a universe that is winding down. We live in a universe that is unfolding. Gravity is the guide that ensures every step of that unfolding is consistent with the second law. It makes sure information is never lost. It shapes the stage so that new phenomena can rise. Perhaps one day we will discover the microscopic architecture beneath space-time. We will look at the universe through its own source code. We will understand how information stitches together the fabric of existence. And in that moment, we will finally see gravity clearly for what it has always been. Gravity is not a law imposed from above. it is a choice made from within. Gravity is the universe giving itself room to grow.